Okay, so just a quick video on the definition of a supremum of a non-empty subset of the real numbers. Okay, so we can define sigma. So there's two definitions. Okay, so first of all, let's define what the supremum is. Okay, so sigma can be considered to be the supremum of a set S if and only if sigma is an upper bound of that set and it satisfies the second condition. Okay, so first of all, before that, let's define what the upper bound is. So the upper bound of a set must be greater than or equal to every single element in the set. Okay, and to be the supremum, it must be the lowest. It must be the lowest element which does this. Okay, so it has to be the lowest number, if you like, that is bigger than or equal to every element in the set. Okay, so the first definition, it doesn't really correspond to the diagram. In fact, the second definition is what corresponds to the diagram here. So we can just have a look at the first definition here. So I can just draw you an interval, and this is my interval S, defined on the real number line, and we can say that sigma is here. Okay, so this is the supremum. It's here. Okay, it's the biggest element. Excuse me, it's the least element which is bigger than or equal to all of these elements in this set here. Okay, so now if we have a sigma dash, okay, so let's say we have a sigma dash here. It's kind of like a pseudo supremum. It's an imposter supremum. Then this first definition says that there is an x member of this set such that x is bigger than sigma dash. Okay, so this is our imposter supremum. We're going to prove that it's not the actual supremum. So the definition tells us that there will be an x in this set that is bigger than this, meaning essentially nullifying the fact that this is the supremum. Okay, so that's the first definition of what the supremum is. The second definition corresponds to this diagram here, so I'll read it out for you. So we can consider sigma to be the supremum of set S if and only if sigma is an upper bound of S, and for every epsilon greater than 0 there exists a y that belongs to the set such that y is greater than, strictly greater than, the difference between the supremum and epsilon. Okay, for every epsilon greater than 0. Okay, so what we can do, so I've just worded it here in a way I kind of found it digestible. So what I've said is that this term here, in fact, let's make it a little bit easier. Let's just say this term here is A. Okay, so in the diagram, I'm going to have this is A, and instead of having this here, we'll just say this is A. Okay, so A will dip into the set. Okay, because you're taking a supremum and you're minusing a number epsilon which is greater than 0. So the supremum, take away a very small value or whatever kind of value it is, it will dip into the set, so it will be part of the set. But no matter how small you make that epsilon, no matter how small it dips into the set, there will be an element of the set in between these two values. That's essentially what it's saying. Okay, so just diagrammatically, I found it really useful, this diagram here. So here we have our supremum, and here we have our value A. Okay, and again, it dips into the set. The reason is that epsilon is greater than 0. That's the reason why it dips into the set. Epsilon is positive, and you're taking away a positive value from the supremum, so it will dip into the set. So the second definition says that there will definitely exist a y that is in between these two values. The y is bigger than A. Okay, there will definitely exist a y that is strictly greater than A, and that's how you define the supremum. Okay, so just two different definitions there, and I hope this helped.